In this problem, we receive an m times n matrix that contains only the values 0, 1, or 2, where 0 represents an empty cell, 1 represents a fresh orange, and 2 represents a rotten orange. Every minute, a fresh orange that is adjacent to a rotten orange in any of the 4 possible directions, up, down, left, or right, also becomes rotten. Our goal is to find the minimum time required for all fresh oranges to become rotten. If it is impossible for all oranges to become rotten, we return -1. This problem can be visualized as a dynamic process where the spread of rot from rotten oranges to fresh ones needs to be tracked efficiently. To achieve this, we can model the problem as an unweighted graph where each cell in the matrix represents a node and the edges between nodes are defined by possible movements in the 4 directions. This graph-based approach allows us to leverage the breadth-first search technique, which is particularly effective for finding the shortest path or the minimum time in scenarios like this. We begin by defining the orange's rotting function, which receives a matrix grid of type vector and returns an integer value representing the minimum time required, or -1, if it is not possible to rot all oranges. The initial step involves determining the dimensions of the matrix by storing the number of rows m and columns n. This setup helps in managing boundary conditions during traversal. Next, we initialize a queue Q to hold the coordinates of the rotten oranges and the variable fresh oranges to count the number of fresh oranges. To populate the queue with the initial state of the rotten oranges and count the fresh ones, we iterate through the matrix using 2 nested for loops. For every cell that contains a rotten orange, grid of ij equals 2, we add its coordinates to the queue. Conversely, for every fresh orange grid of ij equals 1, we increment the fresh oranges counter. This initial population step is crucial as it sets up the starting point for our BFS traversal. If there are no fresh oranges at this stage, we can immediately return 0 since no time is needed to rot non-existent oranges. The BFS process requires calculating new positions based on the 4 possible movement directions. To facilitate this, we initialize a displacement vector tirs, which helps in calculating the new xy coordinates when moving from one cell to another in the matrix. This vector reduces code complexity and enhances readability by encapsulating the direction logic. We then commence the BFS process by initializing a minutes counter to track the elapsed time. The BFS loop iterates until the queue is empty, processing each cell's neighbors. For each rotten orange in the queue, we examine its adjacent cells. If an adjacent cell contains a fresh orange, we mark it as rotten, add its coordinates to the queue, and decrement the fresh oranges counter. This step-by-step infection process continues until all reachable fresh oranges have been processed. The key aspect of this approach is the level-ordered traversal inherent to BFS, which ensures that all oranges rot in the minimum possible time. By incrementing the minutes counter at the beginning of each BFS level, we accurately track the time taken for the rot to spread through each layer of fresh oranges. If after processing all possible rotten oranges there are still fresh oranges left, we return -1, indicating that it is impossible to rot all the oranges. The BFS algorithm is particularly well suited for this problem because it explores all nodes at the same level before moving to the next, thus guaranteeing the shortest path in an unweighted graph. The use of a queue to manage the order of cell processing and a displacement vector to simplify the calculation of new coordinates makes the algorithm both efficient and easy to understand. Returning minutes -1 ensures that the calculated time correctly reflects the actual number of minutes required to rot all fresh oranges. If it is impossible to rot all fresh oranges, the algorithm appropriately returns -1. Now, we need to test this code to ensure it works correctly. Remember that you can test your own ideas, and you're encouraged to test edge cases and try other implementations. This helps you learn better and develop your problem-solving skills.